So we know electrons are always moving, right? Within a molecule, they're always moving. That's how we get like partial positive and partial negative charges in an organic compound, is because the electrons are moving around. So when electrons have double bonds or triple bonds, a resonance structure just means that that double bond sort of moves around. Like there's multiple locations that double bond can go. So in order to know if it's going to have a resonance structure, the first thing you have to do is draw a Lewis structure. So that's what I'm going to start with. In the directions it says, draw the Lewis structure and then include all resonance structures. And then we'll go through and name the molecule, give the electron pair geometry, the molecular geometry, which again, molecular geometry is the shape. And then we're going to indicate a bond angle. So I have carbon and 3 oxygens, and the -2 just means that when everything's said and done, after I've done all of the valence electrons, the Lewis structures, I'm going to have 2 extra electrons that are going to be added in there. So the atom between carbon and oxygen, the one with the least amount, is usually the one that goes in the middle. So I have carbon and I only have 1, and then I have 3 oxygen. So I'm starting with my carbon. Carbon, I'm just going to look at a periodic table real quick. Whoopsie. I'm just going to look at a periodic table. You guys maybe already know this. I already know a lot of it too, but just to show you guys, again, valence electrons are 1, 2, 3, 4, 5, 6, 7, and then 8 from here and down. Helium is 2. So carbon's right here, 4 valence electrons. So I'm going to go back and draw on those 4 valence electrons. Remember, Lewis structures, every side gets 1 before any side gets 2, so there's the 4. Then I have oxygen, so I'm just going to sort of strategically place my oxygen sort of like around the carbon, just nice and spread out. And then I need to know, or I know that oxygen has 6 valence electrons. It's right here on the periodic table, so 6 valence electrons. Again, every side of my oxygen is going to get 1 electron before any side can get a second. And again, I'm just going to do my best to sort of strategically place those 2. Like I'm going to do the lone pairs on the sides that are away from the carbon, just to try and make this look as organized as possible. That dot did not look like a dot. There we go. Okay, so let's make 1 dot there so that there we go. Okay. So then all of the oxygens need to be bonded to the carbon. So all of the lone pairs are not bonding electrons. The electrons that are by themselves are the bonding electrons. So I'm just right off the bat going to go ahead and bond each of my oxygens to the central atom. They all need at least 1 bond to the central atom. So that gives me a few bonding electrons left, right? I have 1 bonding electron here, 1 on this carbon, and then 1 on this oxygen over here. So I have a bunch left. Because I still have 1 bonding electron on my central atom, I'm going to go ahead and pick an oxygen and just bond it to it. So I'm just going to pick this one since it's kind of close, and I'm just going to go ahead and bond that there. So now my central atom is all taken care of. I still have 2 bonding electrons on these 2 oxygen, the one here and the one here. They can't just be by themselves. Before you start like connecting them and making weird like triangles, you're not allowed to do that. First thing I'm going to do is I'm going to check and make sure that I've done my molecule correctly. And as you can see, the molecule has a -2. And remember I said the -2 just means we have 2 extra electrons. So I bet you can guess where those 2 extra electrons are going to go. I'm going to go ahead and just draw them in here so that we can see in a different color where they're going to go. You should double check your molecule, make sure that every element has 8 valence electrons. So starting with this oxygen, I have 2, 4, and then the double bond is 6, 8. The carbon in the middle, each bond represents 2, so 2, 4, 6, 8. The oxygen on the right, both of them, they both have 1 bond, which is 2 electrons, and then 3 lone pairs, which is 8 total. So every atom there has or is sharing 8 electrons. I'm going to write this prettier now that it's all like, organized. I'm going to go ahead and just write it prettier. So here we go. Oxygen, and this one had 3 lone pairs. This one had 3 lone pairs. and then I had a -2 charge. So here, now that I've drawn the Lewis structure, right, this is my Lewis dot. I'm just going to write LD for Lewis dot. It now asks me to show all resonance structures. So resonance, I'm just going to put a little arrow showing that it could be this. So I'm just going to move that double bond around. So I have the oxygen that was double bonded. I'm going to move the double bond up here. That's going to change the number of valence electrons. This one's still going to be a single bond. I'm going to go ahead and just draw all of that in to show all of the possible resonance structures. So that's -2. My double bond can actually go in a third place here. It can go on this oxygen. So I'm going to go ahead and just show that on here. Like this. That'll be a single bond. Oh, whoops, I put too many lone pairs on this one. Right, if there's a double bond that already has 4 electrons, so you only need 2 lone pairs to make 8. And then we have this last oxygen over here. And then it has a -2 charge. So those are my resonance structures. So again, showing that that double bond could have gone on any one of those oxygen. So this happens to have 3 resonance structures. For A, it asks me to name the molecule. So that's a polyatomic ion. So we name it as the polyatomic ion, carbonate. B, it asks for the electron pair geometry. So in order to get the electron pair geometry, I need to count how many things are on my central atom. So here's like 1 double bond, here's a single bond, and here is another single bond. So I have 3 bonds and no lone pairs on my central atom. So I'm going to go over to this table, and I have, what did I say, 3 bonds and no lone pairs. That means that my electron pair geometry is trigonal planar. So I'm going to go back and I'm going to write trigonal planar. And then your electron pair geometry and your shape are going to match if there's no lone pairs on the central atom. If there is lone pairs on the central atom, that's where you start naming it other stuff, right? Like here and here, right? Those are all things where this is my electron pair geometry, and then this would be my shape if I had a lone pair instead of a bond. The one that I put in your notes I actually think makes way more sense than this one, which is the one from your book. So if you'd rather reference the one on your notes, you might do that. Last, it says to give the bond angle. So again, trigonal planar, the bond angle is 120. That, again, the one that I put in your notes shows the bond angles. In your book, it's a different table. So you can look it up if you want, or again, look at the one in your notes. But trigonal planar has a degree of 120. And so that's it. You're going to show the resonance structures for every time. So the most important thing is to do the covalent Lewis structure correctly. Everything else after that is sort of, moving the double bond around, looking up the information for answers A through D if you haven't memorized it yet. But that's about it. There's answer keys on the discussion board, and please let me know if you would like to see any more of these. I'm happy to do them and explain them just like I did that one. Thanks. Actually, if you're still watching, I think I'm going to do number 2 as well, just because I think another example is going to be good. And then having sulfur as the central atom is a little more difficult because you're going to have to split a lone pair. So let me show you how to do that. So again, I'm going to start with the Lewis structures. So, oops, pen, there we go. So I have sulfur. Sulfur is in the same group as oxygen, so it has 6 valence electrons. Every side gets 1 before any side gets 2. And then I have 3 oxygens, just like before. So again, every side gets 1 before any side gets 2. And again, just like I did before, I'm going to space them sort of strategically, just like around it. If you put them all in like one row right next to it, it's going to get really confusing. You're going to have a lot of like crossed lines. So spreading it out like just automatically makes it a little easier. So again, first thing you have to do is everybody has to be connected to the central atom with at least 1 single bond. So I'm going to go ahead and connect everybody. I can connect easy with 1 single bond, and then you're stuck. because that third oxygen can't even connect to sulfur. So what happens is the lone pair on sulfur is going to get split. So how that works is oxygen's little electron here is going to come in and bond with one of the lone pairs, and then this other electron is going to get kicked out and join the other electron on that oxygen. So it doesn't create a double bond. I'm going to show you how the double bond is created in just a second, but that first one, when you split a lone pair, you're again going to kick out that other electron, and then that electron will attach in a necessary place. That same action is going to happen on the other lone pair on sulfur as well. So I'm going to go ahead and just in another color, just to kind of differentiate what we're doing here, I'm just going to go ahead and connect my electron to this other lone pair, and then this electron is going to get kicked out too. Well, the only place for it to attach onto is actually down here. So it doesn't necessarily have to go to the same atom, and that's because, like I said before in the first example, all electrons move around. So as long as they're in a compound, all those electrons are being shared everywhere. So this is really messy. That's why I redrew it before, is because it kind of gets messy. I can double check. There are no bonding electrons left. Every electron has been bonded. I didn't have to add extra electrons. There was no charge. So I'm good to go. So I'm going to draw my sulfur in the middle, and then I have a double bond here, right, with this first oxygen. So I'm going to go ahead and draw that double bond. And then I have a single bond out to this one, right? That dotted line is not a bond. So it's a single bond out there, and then I have 6 more lone pairs. And then again, here's a bond, and this dotted line again is not, the blue dotted line is not a bond. That's just the electron joining the oxygen. So again, it's a single bond. So there is my Lewis structure. So I'm going to draw the resonance structures, which is basically all the places a double bond can go. I just want to say that if you run into a case where one of these oxygen had wound up being like hydrogen, the double bond can't go there. In order for the double bond to move around, it does need to be the same element. You can't just put the double bond wherever you want, especially on a hydrogen, right? Hydrogen only makes one bond, can't have a second bond. So just be wary of that when you're drawing resonance structures. The double bond is only going to move between elements that are the same. So there we go. There's our 3 resonance structures. And this we named sulfur trioxide. Because it's a covalent compound, we use the prefixes, so sulfur trioxide. Remember, you don't use mono on the first element, so it's not mono sulfur trioxide, it's just sulfur trioxide. We have 3 things on the central atom, right? A double bond and 2 single bonds, so that's 3 total, which means that this is trigonal planar. And we have no lone pairs, which means that the electron pair geometry and the shape are the same. And trigonal planar is 120 degrees. So I apologize that those 2 examples had the same like shape, but you guys have done a lot of practice on that, so hopefully that part is pretty easy. The only new thing we're really adding here is drawing the resonance structures. So if you need more examples, I'm happy to do more, but I just wanted to show you one of those where the lone pair splits. So now I am officially done. Please let me know if you have any questions.